of all, a very warm welcome to everyone who have gathered here to just listen to me. I know it's a Sunday evening, and it's not a pretty good time to maybe listen to a talk or something like that. But I would firstly thank Moitreo for this opportunity for making me speak here, whatever I could. So first of all, we would be discussing some good stuff, like not so much academics, but I will certainly share some of my works that I have been developing from the past 1 year in the lab. I am Subhajit Chakraborty, a fourth year undergrad student and a chemistry major here at Department of Chemical Sciences, IISERK Kolkata, as you can see. And the lab that I work in, it's called the Sensitive Lab under the supervision of Professor Swadhin Kumar Mandal. And why it's sensitive and why is it so, we will all look into that. The title of the talk is Seeking the Lows. Why is that? There is a significant reason behind that. You might have, all of you, or might have or may not read the abstract that I had written, that was written in my poster, in the poster that was shared to you for the talk. And the words written there are written in sarcastic tones. In some places, I have tried to. Is it visible? It's all right, right? I heard one notification just now. Let me. Is it fine? Okay. Yeah. Yeah. Sure. 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 Okay. So I will continue from where I left. Yeah. In the abstract, I have written something sarcastically, something about the chemistry education policy that we follow in India. Yeah, I have sufficient reasons for speaking bad about it or sarcastically about it, because after joining IISER Kolkata and studying advanced chemistry and being actively involved in research, I have found that there is a lot of um, like not so good things happening around in the education system, especially for chemistry, that has been followed in schools and in coaching centers, and also the pattern that is followed in the foremost entrance examinations, the so-called the famous entrance examinations. It's also not so much of worth just to test the chemistry aptitude and knowledge. Okay, so we will talk about that also. First of all, before starting the chemistry discussion, let us first bow to the Lords. Now, you may question who are the Lords. The Lords are basically no one but the Chemistry Nobel laureates of 2022. Needless to mention, the three legends, Caroline R. Bartoszi, Morton Mildel, and Barry Sharpless. Caroline is from Stanford, Morton is from University of Copenhagen, Denmark, and Barry Sharpless is from Scripps. So all of them are, you might know them for what they have got the Nobel Prize of Chemistry in 2022 for the development of click chemistry and bioorthogonal chemistry. Maybe we can plan another session just to discuss on that. But today is different. Now, I want you to look at this. What's this? This is a thing that every chemist should have in his purse or his or her purse. That is the modern periodic table, right? It's very simple. All of us know that. Or we have been exposed to a periodic table for a long time now, and many non-chemist people will also recognize it. And let me take my pointer here. This work, the function of my pointer starts from here. Now, if we look at it, we can find two extreme corners, the left one and the right one, right? We have some series of elements: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, beryllium, magnesium, calcium, strontium, barium, radium. So these two and these groups, starting from 13 to 18, they fall in the p block elements, and they are the s block elements, and together they form the main group elements. Why? One of the foremost reason is that they are found in abundantly in the earth's crust. Okay, if we compare the middle portion that is marked in blue, those are the transition metals or the rare earth metals. They are found in very less quantities in the earth's crust. And what is the effect or significance of this quantitative measurement present in the Earth's crust? That also has many things to do today. That has many significance. What are those significances? We will talk about it as the talk goes. Okay. So going forward, First of all, when we listen to the word main group chemistry or inorganic chemistry, main group inorganic chemistry, the common notion I have uh, found in many people, many students also, many researchers also, it's that it's so boring. It's what's new in there, what's new to what is new there to find out, right? What is new? Everything has been done because main group chemistry, as honestly to say, it's the one of the oldest branches of chemistry. As soon as modern chemistry started, with the start of alchemy, main group chemistry started hand in hand. Okay, very old, very traditional chemistry techniques. Needless to say that Cameron Jones, one of the foremost leaders in the field of main group chemistry, has quoted this in his own words in an interview. I have quoted them. Within inorganic chemistry, he's saying that. Just see what he has said. Within inorganic chemistry, main group was the most boring part of my undergraduate degree. At that time, it was thought that everything we needed to know about the chemistry of the main group elements was known. The properties, oxidation states, and reactivity were pretty much developed, and there was no new areas to go. Absolutely. Now we can agree that why to study main group chemistry. Cameron Jones. The irony is that he is now one of the greatest leaders in the field of modern main group chemistry. Just see the irony. It's funny, right? The guy is telling that in his undergrad days, main group chemistry was the most boring part, and now he is the leader of the field. So anyone is exploring. My abstract also tells this at last. I have tried to correlate this. That's why. So going on. So the question is that the more significant question that comes to my sarcastic notion part that I had mentioned in my abstract is that what has made Cameron Jones and people like us uh, hate the main group chemistry, or what has instilled this boredom that we have for main group chemistry in our minds? What is the root of this thing? The uh, According to me, it's my personal opinion, the only thing that has made this possible is the design of the present curriculum that we have for inorganic chemistry and chemistry as a whole in the plus 2 stage. Simply, many non-chemistry people who are, if they are present here, might relate this with me. Like if they are preparing, if a child is preparing for like any sort of competitive exams, namely NEET, JEE, or something like that, they join coachings, and if we analyze the previous year papers, we all have given these exams. The inorganic chemistry portion does just consists of direct questions that are being asked from the NCERT textbooks. And what is the syllabi of these textbooks? Let's look at it. This is the class 11 syllabus. Just see S block and P block elements. These are the inorganic chemistry main group chapters that have been covered, and trust me, nothing's there apart from just informations. And what are the students doing? Just cramming up and just putting those values in their mind, putting those reactions. They are doing just ratta. They are just cramming up the reactions and then ticking up MCQs. What is the like result of this? As a result of this, for the almost 4 decades, main group chemistry did not see any sort of like modernization, or so as to say new research areas that could emerge from main group chemistry. No one was there to do anything because no one was interested at the first place. And also, if you look at it, the plus 2 like class 2 chapter P block elements, the fault is itself in the syllabi. It's not the fault of the students. It's the fault how they are being taught the chemistry. So that was the main thing I had problem with, and I think this needs to be uh, kept looking at. Okay, otherwise the main group chemistry, how no, doesn't matter how much modernization has took place, students will not be there to realize this. Now, going to the solution part, we need a solution for that. And the solution was thought of a long time ago, and there was a need for modernization and a new start. And any scientific discovery just starts with a simple question. That's why I always ask my juniors, and also I like very much the people who ask interesting and good questions. With good questions come great answers that could be revolutionary. And this happened in this case also. The start with the increasing interest in the scientific community started with a really simple question. We know that every group in the periodic table have a group valency and a maximum oxidation state that an element can attain, right? What if we try to temper the group valencies and also the oxidation state of the main group compounds? It's a pretty simple question, right? Let's say, for example, we have a group 13 element, let's say boron, and we have a compound of boron, namely let me take boron trifluoride, BF3. You can tell that boron is in plus 3 oxidation state. Is the maximum oxidation state that boron can attain. So the question they asked is it possible to access the lower oxidation state like 0, 1 or 2? Is it possible to go down from 3 to these three numbers? The answer to the question, the people started to look for the answers. And the answer they got was indeed awe-striking. Just they it left the scientific community bewildered for a long time. And the quest for such species, like where the oxidation state could be lowered, started. And it was seen that the answer was not so trivial. It's not so easy to make these compounds. They didn't even know if these compounds could be made or not. Just leave alone the thought of like stabilizing those compounds. So with this, we can say that the quest had started the modernization. So what next? So you have heard about the low oxidation state chemistry, right? So what's this? Just I will take some simple examples. Is someone saying anything? Okay, yeah. So for to just explain what is the low oxidation state chemistry or the low valent chemistry, I have taken some extraordinary chemistry examples just to make you understand in a very simple term. Let us look at these molecules. Okay, chemistry is better understood when you look at the molecules and just try to analyze them very simply. So what is this? It's a boron compound. Both of them are boron compounds. One of them is called the diborines because it looks like an alkene, but the carbon atoms are replaced by boron. And it's a diborine where the carbon atoms are replaced by boron, but it looks like an alkyne moiety, right? So here you can see that boron has an oxidation state of +1, and here boron has a zero oxidation state. So you can see that the answers to the very fundamental question was getting to get answered. Like the answers were starting to come from different scientific minds. Like this was prepared by Gregory H. Robinson, and this was synthesized by Holger Braunschweig. Okay, so they already answered some of the questions. That yes, boron 1 can be prepared, boron 0 can also be synthesized. So what about the other main group compounds? Yeah, they also answered it. Like these are the carbene moieties. The carbon has an oxidation state of +2 divalent carbon centers, and all of us know what carbenes are. Any non-chemistry people who have studied organic chemistry in +2 have studied about carbenes. Riemann-Timan reaction. We study the formation of dichlorocarbene, and from where we study very basic chemistry, right? And now carbon 0 is also there. Guy Bertrand reported the formation of the first carbon 0 compound and named it as carbones or the carbodicarbenes. Here you can see that it's an isolated carbon atom where the oxidation state is 0 and it has all the 4 electrons to it as lone pairs, two lone pairs. And what's this? This is a phosphinidine system. And the phosphinidine phosphorus has an oxidation state of +1. Oxidation state of phosphorus is commonly 3 or 5, but we have phosphorus 1. So the answers were clear, and it's very much appealing to our eyes that, yeah, the lower oxidation state is possible and the compounds can be synthesized too. So what? Now you can question what is the use of okay, I will synthesize these compounds, but after that what I will do with that? It's extremely difficult to synthesize these compounds. As you can see that the oxidation states are very much unstable, so they will try to go to the higher oxidation state. They will not try to be in boron 0. As soon as it gets a chance, it goes to boron 3. So what might be the reason behind that? Why should they go to the higher oxidation state? They have excess of electron density to them. Once you lower down the oxidation state, you are giving excess electrons to these moieties, right? They are willing to give their electrons to someone. So what are they? They become extremely nucleophilic, extremely electron donating. As soon as they find electrophilic centers or electronically deficient centers, they immediately react and donate electron density and make themselves stable by attaining the maximum group oxidation state. So what? Now we will go to the mainly so in this talk I will mainly try to cover the chemistry of carbines because it's a very large area of topic of research that I have been doing in my lab, and our lab does this a lot, carbene chemistry. So what are carbines? The carbines are very cool. uh, the it's needless to mention, right? So what we do, we try to harness extremely sensitive low valent carbon species like carbon 2 or carbon 0. Mainly, we try to synthesize a particular family of divalent carbon species, and they are commonly called the carbines, as you will know that. But wait, that synthesis is a different thing, and to isolate and store the carbene in a bottle is a different thing. Okay, so storing the carbene is not so easy. In Reimer-Tiemann reaction, we see that dichlorocarbene gets used up in the reaction. It is not isolated. We cannot make the carbene and store it in a bottle. Why is that? There is a big problem in that. The dimerization is one of the most major problem that we have. Once the carbene forms in solution, the species dimerizes readily to give olefinic species. And what is this dimerization? I will show in the next slide. And we lose the isolable carbene species. So what? So what is the solution? We need to solve this. This is a scientific problem, right? We need to make the carbene in such a way so that I can take it by my hand, synthesize it, and store it in a bottle and show to everyone. Just see, I have made the carbene. Okay, but it's not so easy. It's a divalent carbon. Carbon needs to have a valency of 4, and it needs to get to an oxidation state of +4, right? We need a kinetic. So what is the solution? The solution that scientific community thought of is that we need a kinetic protection to stabilize the carbene center. Okay, what is this kinetic protection about? We will the study of this, or the then it's again a question, right? What is the kinetic protection? What's the kinetic protection that we are talking about? It's again a scientific question. See the how the questions were developed step by step, and to find out the answer to this question started the development of a new whole domain of chemistry called the n heterocyclic carbene chemistry. And what's that? We will discuss in a minute. So here that you can see is the first example of an isolable carbene. Like he prepared the carbene and stored it in a bottle. How did he do that? There is a uh, simple chemistry. Just he took the imidazolium chloride salt of this adamantile substituted imidazolium, and then he treated with a base, sodium hydride, in presence of THF and catalytic DMSO at room temperature to form this carbene center. This hydride takes H from here and forms H2, and we have Na and Cl, formation of NaCl salt, and we have the formation of carbene here. So he saw that this carbon species doesn't dimerize. The problem has been solved. How it has been solved? Very easy. As you can see that these substituents are so bulky, very much big in size. So how the dimerization takes place? Two carbene moieties approach each other from two sides, and they exchange electrons and form the dimer, right? So if in somehow we can stop the two carbene moieties from coming close to each other or coming close in proximity to each other, we can stop the dimerization. This is exactly what has been done. The substituent size has been increased so that there is excessive repulsion between these adamantine rings. Like sort, let's imagine that one more carbene moiety comes from the upper side, and these adamantine rings are there, so they face excessive repulsion, and due to this they cannot come close to each other, and the dimerization is prevented. Simple chemistry, yet so beautiful. And this gave to the revolutionary discovery of isolable n-heterocyclic carbene. First example of the carbene that has been isolated and kept stored in a bottle. This is the crystal structure, and it's an open question to the audience. The base abstracts this hydrogen, right? So what is the role of this catalytic DMSO? In many organic reactions, people have seen that DMSO acts as a solvent. In any reaction, right? DMSO is a solvent in maximum cases. So why this is catalytic DMSO? What might be the catalytic role of DMSO? It's an open question to the audience. Everyone is welcome to answer. I would really appreciate it. This explains that you are thinking the things in a good way, in the right way. So I would like to just let you know that the dimerization has a name. The carbene dimerization follows an equilibrium, and that is called the Wanzlick equilibrium. See, once the carbene forms, it's an alpha elimination. We have the elimination of chloroform, and we have the formation of this carbene. Two molecules of carbene approach one another from opposite sides, and this is the equilibrium that guides the formation of the dimer, the olefinic dimer. See, so they have done, they have enlarged this R substituent, and this pushes these two moieties away from each other, and we have the isolated carbene. Pretty simple. The direction of this equilibrium can be tuned by tuning the N substituents that provide kinetic stability to the monomeric carbene center, and hence the backward reaction is favored. Exactly what we have discussed right now. So moving on, so there was now these type of carbenes where the C2 carbon center is having the carbene. This is the C2 carbon, right? If we mark nitrogen as 1, 2, 3, 4, 5, this carbon is the C2 carbon, and it has the carbene, so it's a C2 carbene, or a normal n-heterocyclic carbene. So now scientists wanted to see that what is the effect of the base on the other hydrogens present. Here is also one hydrogen, here is also one hydrogen, here is also one hydrogen. So C2, C4 and C5 have all hydrogens, right? Is it possible to selectively deprotonate the C5 hydrogen? Okay, that's another question they asked. See, every question they are trying to find out answers, and they are making revolutionary discoveries. So it was a bigger challenge, obviously a bigger challenge. The first challenge was due to the lower acidity of the C5 proton compared to the C2 proton, right? Exactly. Let me go back to the picture. If you see, the C2 proton here is masked by two nitrogen atoms. As soon as we this hydrogen will be more prone to deprotonation. Why? Because the carbanion will be more stable due to the presence of this minus I affecting N groups. They will lower down the electron density and stabilize the carbon ion formed. But here C5 deprotonation is difficult because it is only stabilized by one nitrogen atom and another carbon atom. So not so strong inductive effect, right? So pretty much very difficult to deprotonate this hydrogen in presence of this hydrogen. So they took beautiful steps. See here, I have written this. The C2 position and the C4 position need to be protected to have the required C5 centered carbene. Let us see the picture. See how beautifully they protected the C2 position and C4 position using phenyl group. See, so the only option the base is left with is the C5 proton, and that is exactly what happens when they treat this salt with the let's say potassium hydrogen dimethylsilyl base KHMDS. What happens is that the base selectively deprotonates the C5 hydrogen, and we have the carbene at C5 position. And such type of carbene moieties were first synthesized and reported by Guy Bertrand and his group at Paul Sabatier University, France. And for that they published a science paper, and it was very famous. And our SKM group, like our lab at IISERK Kolkata, was one of the first labs to synthesize and stabilize this molecule in the lab, and and to do catalysis with that. It's a very big challenge to synthesize this compound because it's very much kinetically and thermodynamically unstable, because you are deprotonating a less stable as proton. But they have done it beautifully by blocking those C2 and C4 positions. See, here you need uh, like a good sound knowledge of synthetic organic chemistry to synthesize the salt itself. So after preparing the carbene, why did they prepare? There must be some reason behind that. They saw that it was more nucleophilic and a better sigma donor and pi acceptor, and hence a better ligand design to stabilize the low valent species and to activate small molecules. Exactly. It has to happen for some reason, right? Anyone can then make any molecule and say that I will make that. But why should I make it? Why to take so much risk and to take so much challenge? Because it's better as a ligand. Okay, it's very much nucleophilic compared to the normal carbenes, and these family of carbenes are also called mesoionic and heterocyclic carbenes or the abnormal carbenes. And my research work mainly focuses on the study of abnormal carbenes and the chemistry associated with it, and we will discuss it in a shortly in the upcoming slides. Yeah. So so I have told you that it is more nucleophilic. So why should you believe it? There must be something to prove it, right? So they have measured the nucleophilicity parameter using a mathematical tool that directly correlates with the bond stretching frequencies derived from a two-body harmonic oscillator problem. Like many of who have taken organometallic chemistry courses, we have heard about carbon monoxide or nitrosyl NO stretching frequencies, right? Any bond, covalent bond has a stretching frequency, and with that stretching frequency comes from a two body harmonic oscillator problem, and that is called the Tolman electronic parameter. It's a mathematical parameter that is measured in terms of centimeter inverse and that comes directly from that bond stretching frequency. I have just added it in a little short so that you have a gross idea. If you want to discuss it with me later, I will be happy to do so after the talk. No issues with that. Now, due to time constraints, we have to go about it. Okay. So the Tolman electronic parameter is given by zero point 0.8, roughly given by. Okay, it's in a rough calculation. It's not exact. It's 0.8001 new average, where new average is the average of the all the bonds significant bond stretching frequencies that the ligand is affecting plus 420 centimeter inverse. Okay, so this is a chart that has been showing many carbene moieties and other ligands having the Tolman electronic parameters written to it. The rule of thumb that we follow is that greater the Tolman electronic parameter, greater is the stretching frequency, and the worser the ligand is. The ligand is less donating, less nucleophilic, so it has a high TEP value, that is the Tolman electronic parameter value. So if the ligand is very much nucleophilic, the Tolman electronic parameter should be less. So it has been seen that for abnormal carbene, the Tolman electronic parameter is almost about 2033 centimeter inverse, which is much lower than the normal carbene. So this clearly proves that the abnormal carbene is a better nucleophilic and a better sigma donor pi acceptor compared to the normal carbenes. Okay, just to give you a taste of how this nucleophilicity is measured of different ligands. If you want to discuss it with me later, we can discuss it in detail. So why to synthesize these molecules? Let's come to the applications. Without applications, we can't just rationalize the synthesis of a molecule, right? And that too, which is too much difficult, too much challenging to synthesize, extremely air sensitive. Once it gets exposed, it gets quenched. Obviously, so this table, it makes me proud to say that this is the table that has been solely like explored by our group in very much detail, and no corners have been left, and still the studies are going on. The NHCs which are applied to the P block elements and also the other low valent main group compounds. Mainly, we work on activation of small molecules and the frustrated Lewis pair chemistry. These two are the areas where I work on or I have been working on, and these are the two areas, other areas that my seniors and other PhD students have been working on for a long time. You can check out our website. There are many works given there, many papers there. You can read it. You can get as much amount of knowledge or ideas you want to. So thanks to my professor, Professor Swadhin Kumar Mandal, and our group, that we have been doing the excellent chemistry. Now, I would like to draw the attention if there are any organic chemists present in this field, you might relate with me that there is an has been an increase in the use of NHCs as organocatalysts also. Okay, they have been used as Michael acceptors, used with aldehydes to give different types of Bailey-Hillman reactivity or stator type reactivity, or like formation of Breslow intermediates. You can see that this is a Breslow intermediate. What I am talking, I will not talk about Breslow intermediates in detail. That can be found in any organochemistry textbook, standard organic chemistry textbook, or you can Google it also if you want to know about it. So, Professor Frank Glorious has been doing excessive chemistry with NHCs as organocatalysts. And also, you can check out the group website of Akkatu T. Biju, Professor A.T. Biju of IISc Bangalore, Department of Organic Chemistry. He is also the postdoc student of Frank Glorious. He has been doing excessive chemistry using NHCs as an organocatalyst. Okay, so it's an extremely interesting area of research. Trust me. So, what are the main group species that we have been stabilizing so far using abnormal N heterocyclic carbons? So, I present to you the two main compounds that we have been working about in our lab. So, we have stabilized mesoionic N heterocyclic olefin. You can see that there is an exocyclic CH2 minus. This is a resonating structure. If you push this arrow, you will have an exocyclic double bond, and here too you will have an exocyclic double bond N, which is also known as the mesoionic and heterocyclic imine. And you can check out, there is an Anguwanti Shemi paper that has been published recently from our group, and this has an inorganic chemistry paper. And I will not discuss what has been done with them in detail, but you can check it out. I just wanted to show it. So these are the main group species that we have been stabilizing, and trust me, more are on the way. Just wait and watch, and we will stabilize the rest of the p block. We will leave no stones unturned. Okay, each one of the p block elements will be covered, and each one of them will be stabilized in their low valence state. So what we do, another aspect is the my area of research, or what I have been interested in is a part of organocatalytic small molecule activation. So what are the small molecules that we look at? Hydrogen, dihydrogen, carbon dioxide, sulfur dioxide, nitrous oxide. One apart leaving dihydrogen behind, we can see that the rest remaining three gases have a common relationship among them. You might relate that they are present in excessive amounts in greenhouse as greenhouse gases, right? And one of the most dangerous contributor of global warming is the carbon dioxide. It's increasing day by day. We need to control it. And this is what we do exactly in our lab. Yes, we do it. So, why the need? The common connection between these gases is that they are all greenhouse gases. And also, if we can harness these gases and make useful chemical products out of them, we can control the amount of these gases in nature, and also the increment in global warming can be controlled. The most important significance of our research. These and also these are very much inert gases, no extremely non-reactive. They do not want to react with anyone, and activating them is itself full of thrill and adventure, and gives a lot of satisfaction as a chemist. Yeah, that's true. Once you synthesize a challenging molecule and do something bewildering chemistry with it, you can get the joy. Like you will feel like dancing in the lab. Okay, that's not preferable though in a chemistry in a synthetic chemistry lab, but you will get that satisfaction. Like the experimental chemists can relate with me, or the synthetic chemists can, irrespective of any field. Okay, so you can see that the if we look at the annual greenhouse gas index, it's a little bit old, the data is, but it's still significant to see the trend that CO2 radioactive forcing, which is measured in watts per square meter, right? Yeah. Okay, it's increasing day by day, and it's close to one in, like, as far as we have come to 2021, it should be more than one right now. Okay, what I have the intuition about. So it's not so good, it's bad. We need to control it, and we are trying to do that only. So how we do that, I will put up a simple example before you. What is the main idea how we do that? This is a cutting that I have brought before you. It's from a paper that we have recently published, and is the formylation of amide. See, The NH is, we have scissored it with a CHO moiety. The formyl moiety has been stitched with the amide. Okay, so how, where this formyl moiety comes from? Exactly, it comes from the carbon dioxide. Isn't it great? We are harnessing this carbon dioxide, and using that we are installing the formyl moiety from that carbon dioxide. Why, how we do that? We do detailed mechanistic investigations also. No one can prove that we are talking shit and it's vague. No, 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 not at all. Firstly, we take the n heterocyclic carbene moiety, the abnormal carbene. Okay, that is more nucleophilic. So it's so much nucleophilic that it also attacks the carbon center present in carbon dioxide. Okay, the vacant pi star molecular orbital it attacks, and it activates to generate this uh, carbamate moiety, the abnormal carbamate moiety. And the formation of this moiety has been proved by the 1H and 13C and GC experiments. Okay, so then after that what happens, we treat it with one equivalent of silane. Okay, trialkyl silane. So what this silane does is it transfers one hydride molecule here, and this silicon takes this carbamate moiety and leaves the catalyst behind. So we have the formation of the abnormal carbene moiety back into the cycle. So it's a catalytic cycle, okay, where the catalyst is the abnormal carbene. So what we have as product is this silicon formate. What this silicon format does is it's not so stable, and it has been proved by 1H and 13C NMR data. This, in presence of another equivalent of trialkyl silane, transfers this formyl moiety to the amide and forms this siloxane, trialkyl siloxane. And this has been proved by 1H13 and 29 silicon NMR and also X-ray crystallography. We have all the data present. If you want to see it, you can visit this paper, Chem Society Review, that has been published in 2020 from our group. So see, it's a beautiful reactivity. We are capturing carbon dioxide, harnessing it to transfer this formyl moiety from carbon dioxide to the amide. And also mind it, the amide activation is not so easy. Okay, moving forward. Now, the madness that I am into, what I am interested most about, the molecule that I make every day in lab, not so every day, because it making it is very difficult. It's extremely sensitive and also difficult to make. So I call it madness because I do it, and yeah, it's great fun. Is the phosphinidine. I showed you the phosphinidine molecule somewhat back. Is the phosphorus 1 molecule which is stabilized by a normal carbene. See, this is the phosphorus 1 molecule. It has two lone pair of electrons as a negative charge and a negative charge. So you can tell that this phosphorus is extremely electron density. So what stabilizes this phosphorus is it's a the carbene, the sp, this is singlet carbene. So the sp2 hybrid orbital has a pair of electrons which then is pushed into the vacant p orbital of the phosphorus center, which we term as the sigma donation. And then what happens, the another filled p orbital back donates this electron density to the vacant p orbital of the carbene center. So it's called the pi back donation. So this is how this moiety is stabilized. So this is the example of one recent paper that we have published from our group, and this is with the normal phosphinidine. Similar type of reactivity, the formylation of amide, but using this phosphinidine, which also proves that this is also an efficient catalyst system to harness CO2 and other small molecules like that. So now we are what we are doing, we are trying to harness SO2 and N2O in the same way. The work is going on, like we are expecting to get some good results. Once I get that, I will be back again here to talk about it also. No worries. So this is the family of molecules I love the most, and I am intrigued about, not because it can activate small molecules but because of other reasons too. It's extremely nucleophilic, efficient catalytic system for the activation of small molecules. And the other reason that I was talking about is this. It can also act as potential candidates for metallomimics. Now you might have heard the term and also might ask me what the hell is a metallomimic, right? So let's see. Metallomimetic chemistry is now in the trend. It's the new solution. Why I am talking about the new solution? You might be interested to look at this periodic table. Just look at it. It's a periodic table that is made up of according to the natural abundance, and look at the abundance of these transition metals. It's pretty poor. It will get extinct very fast. Okay, in some years, if we just don't lower down the use of or cut down the use of transition metals, we will have no other transition metals left in our earth's crust. That will be bad, right? So, and a solution needs to be there. What to do? Let's see. So this is a typical mechanistic cycle of a Sonogashira cross coupling reaction. Every one of us has read the Sonogashira reaction, right? So let alone Sonogashira, any transition metal catalyst reaction has two major key steps. See, oxidative addition and reactive elimination. So what drives forward these two steps is the subsequent oxidation of this metal center and the subsequent reduction. Metal center PD0 first goes to PD2, and then, and which we call as the oxidative addition, because this PD is getting oxidized to palladium 2. And also we have reductive elimination, that means PD2 gets back to PD0. Okay, so it gets reduced. So we can clearly mention that there is an oxidative or oxidation state switching, like it goes from 0 to 2 and then again from 2 to 0. Can we do that using the phosphorus center also? Because we can see that phosphorus can switch between, or phosphorus has two oxidation states, very common, 3 and 5. So can it be done that the switch can be done between 3 and 5 oxidation states? Yes, it can be done. So this is the famous meme that I tried to put it up. Maybe not so significant here, but thought that it would be funny between a boring talk. It would be nice to see Drake. Okay, so yeah, this the end of this era has come. Now we have to get back to this. Yeah. So yeah, it's possible. It's reported. Here's the paper, and it was extremely interesting to me. So I started looking at it from my point of view of reactivity also, and I am trying that. Here you can see that phosphorus 3 center gets oxidatively added to go to the phosphorus 5 center here, and then exactly mimicking the transition metal palladium, it goes to phosphorus 5, from phosphorus 5 to phosphorus 3, and that is reductive elimination. Absolutely gorgeous and amazing, right? We will be able to mimic the transition metals. Isn't it super cool? We can just cut down the use of transition metals and do like transition metal like coupling reactions using phosphorus centers. Isn't it amazing? Yeah, the field needs to be more explored. It's just one paper, but it needs it's a way ahead. Like it's the first step towards transition metal free oxidative cycles, right? Oxidative or redox cycles. Going forward, it's the last slide of my talk today. I know that yeah, it's never the end, but we have to cut down it because of some try time constraints also, and also I don't want to stretch it longer. So what more madness that I'm going to do? Everyone call me like a sort of this only, because I spend most of my day in the lab apart from my hobbies. So I'm trying to stabilize the abnormal phosphatidine now. Till now I have been talking about the normal phosphatidine having the normal carbene, but now I am trying to synthesize and stabilize the abnormal phosphatidine. It has more other I think that it has more capability than the normal phosphatidine. Let's see. And I will subsequently carry out small molecule activation as we do catalysis from them, main group compound stabilization, and also I'm trying to recreate this phosphorus redox state switching, and also trying to mimic the transition metals. Work is going on. Soon we will be able to share some results, and I would be happy to be here again. And another thing to add, that I do detailed mechanistic investigation by myself. I have been doing theoretical calculations. I do the DFT calculation. I have been running jobs, and yeah, it's very fun to do that. I have been recently learning about all these things thanks to one of my seniors in my lab. Uh, and so, yeah, the last acknowledgements slide that I could think of is the photo of these guys. It's all because of them that I go to labs every day, that I'm motivated to go to the lab every day at 6 a.m. or 8 a.m. in the morning, and work till 8 a.m. in the night or something like that, be in the lab, get joy out of making this challenging molecules, synthesizing extremely sensitive molecules. My sincerest thanks to my professors Swadhin Kumar Mandal and every one of these amazing seniors that I have got, because I am the youngest member of the lab and every one of them are seniors to me. So it's always nice to have someone to guide you through, right? So do visit IISER Kolkata sometime. I know it's very close to IICS Kolkata. I have been there. I have visited there. It's very nice. And yeah, it's a lab. Some of the photos I could find out. You can see more other photos in our website also. This is the heavenly abode that I live in, IISER Kolkata campus. It's absolutely gorgeous. This is the research building that you can see here. This is where all the chemistry happens. This is also the research building. The photo has been taken from the famous research complex lake. This is the place where it all happens. I hope that I could relate or correlate between very abstract topics of chemistry education, problems with that, and then relate it with main group chemistry and the work that I do in the lab. Okay, thanks a lot. And I encourage all of you to ask a lot of questions because I am ready for it. I've come prepared. I know that, yeah, chemistry, like everyone has, should have questions. And like for organic, those people who are organic chemists or also like to have detailed mechanistic explanations, have to have a mechanistic application investigations, or like to go approach chemistry with mechanisms, I would encourage all of you to study or look at this book also, Arrow Pushing in Inorganic Chemistry, an excellent book by Obhik Ghosh from IIT Guwahati and Stephen Berg. I read this book and this changed my perspective towards main group chemistry. I trust that this is one of the best written books. If you have further questions or anything to discuss with me, you are welcome to send a drop an email. These are my email IDs. My sincerest thanks to ISS UG seminar series and also the BSMS community for having me here. Special thanks to Moitreo. He responded so early. I told him that. Yeah. So thanks Moitreo and thanks a lot everybody. Yeah. So the floor is open for questions. Yeah. 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 This one, right? Yeah. 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 They are decreasing. Yeah. This is the more challenging, but this is what the more challenging work is, right? Because you can understand that these metals have d orbitals and the d orbitals are much more easily accessible. You can access them, you can control their reactivity, but p block elements have only p orbitals, energetically very much not so much accessible by molecules. Okay, not so much accessible, it's difficult. So but once we are able to do that, it's revolutionary, right? You can understand that you can cut down the use of these molecules, and that is what I am looking into currently. Yeah. Yeah. It's very novel chemistry. It's very, yeah, 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 yeah. Exactly. Yeah. Yeah, 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 sure, sure. Hmm. Yes, 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 yes. That I want to tell you. Our lab is very much particular in having detailed mechanistic investigations. In all of our research papers, if you see that are being published, you will get a clear cut idea of each and every energetic stability of the molecule. Like energetics of the molecule is clearly given in terms of numericals. Like you will get values, exact values of homolumo gaps, the molecular orbital energies. Then you can correlate them exactly to understand, yeah, that is happening. We give a clear picture of molecular level that yes, this molecule is it's like a play that you can see all the characters coming to the stage. Okay, like let's put it this way. DFT is such a thing, it's beautiful. Like it gives you the clear picture of what is happening. Yeah, that we do. Obviously, absolutely, we do that. Yeah, 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 sure, 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 sure. Yeah, it's a very well known reaction. It's a very well known reaction. No, no, no. This reaction, it's a name reaction. It's called Sonogashira cross coupling. But these this is a reactions. This is a mechanistic cycle on the left hand side, and this is also a mechanistic cycle. Exact copy of it, but replacing the metal with a phosphorus. Yeah, yeah, yeah. Let's see. The innovation is in this step. See here, palladium zero gets oxidized to palladium 2 here. So, and this aryl fluoride gets added. So it's an oxidative addition. And then it gets reduced to 0 again. So you can see that there is a switch between 0 and 2 and 2 to 0, 0 and 2 and 2 to 0. That's how the catalytic cycle continues. Here also, they have been able to show exact same thing but with a phosphorus center. Yeah, this is revolutionary. Yeah, this is a revolution. Yeah, yeah. Here phosphorus is 3 and then it goes to 5 and then again it comes back to 3. So isn't it beautiful? It's beautiful. Yeah, it's beautiful.
Hi, Subhajit. It's a really nice talk.
Yeah, yeah.
So,
May I know
I'm
your
actually,
name, please?
yeah, yeah. I'm actually non from IISERK and I'm currently in the ninth semester.
Yeah, yeah, sure, sure. Yeah, yeah. Go ahead.
So,
Yeah.
yeah. So, I just have a small comment. So, in that paper, we were talking about formylation of amides.
Yeah,
So,
yeah.
what is
Hmm.
the carbene precursor that you use? If you, yeah, yeah.
Yeah, yeah. I will tell you in it in detail. It's the like 2 and 4 phenyl protected imidazolium salt,
Mm-hmm.
the
Mm-hmm.
chloride salt of the imidazolium chloride,
Mm-hmm. Yeah.
where
So,
we
you use the base to deprotect, right?
yeah, yeah, let's say we do not have the carbene here, we have a proton there, right? Just
Yeah.
imagine we have a proton there. You can see my cursor, cursor, right?
Yeah. Yeah.
Yeah, here is a proton. Now you put base in there and the base selectively deprotonates this C5 position,
Yeah.
so you get the
So,
carbene here.
yeah, so your 5 mole percent, that is the carbene or is it the precursor salt?
The 5 mole percent is 16, right? So the 5
Yeah.
mole percent is the catalytic loading of this carbene.
Okay.
It's used in catalytic amount, like 5 mole percent.
Yeah, but now
Yeah.
if you compare the metallic variants,
Hmm,
the
hmm, hmm.
catalyst loadings are like around 2500 ppm, which translates to roughly around 0.025 mole percent. So compared to that, you have 5 mole percent, and that to 5 mole percent of your reactive carbene. So you're
Yeah.
definitely going to use a more, at least a little bit more amount of the precursor salt, the imidazolium salt, right?
Yeah. Let's see that there are many like disadvantages of synthesizing this carbon, because I've been doing this for a long time. It takes up a whole day. The thing
Yeah,
is
yeah.
that yeah, like once it's very difficult because it's but just trapping this carbene is thermodynamically very like an uphill process. You need to lower down the temperature of the reaction mixture before adding the solvent. Like what
Mm-hmm.
you do in the globe box, you take the salt in a slink. Okay, you take the salt and you just add the base. As soon as you add the base in solid state, the reaction starts. It's so fast, it's very much facile. But as soon as you add the base in room temperature, the carbene gets rearranged to a different product. Like how can I explain to you? Like if this is diisopropyl group, okay, the phenyl diisopropyl.
Mm-hmm.
So diisopropyl has a CH which gets activated at room temperature. That is the main
Yeah,
problem.
yeah, yeah, yeah.
So you will get the carbene quenched. You will not get the carbene; it will be quenched.
Yeah,
So the
that's right.
problem is that to prevent that pathway, we have to take a little bit amount of like a little bit more amount of salt, okay,
Yeah.
as compared to the base, because you are losing some of the carbene there also.
Yeah,
So let's say,
exactly. So
yeah,
that's like a kind of a gimmick. Like I was thinking, like 5 mole% writing that,
yeah,
like,
yeah, you got it right. Yeah, yeah,
yeah,
yeah, yeah. I
yeah,
should have
and
made this clear. Yeah, yeah.
yeah, that's fine. And the second point is like, even with transition metals, the
Hmm, hmm,
reducing agent is
hmm.
always silent, right? But there are like
Yeah,
so
huh.
many difficulties with silence. Like you cannot
Yeah,
use
yeah, yeah, yeah.
water, you need to use
I,
molecular sieves and all
yeah,
those stuff.
yeah, 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 yeah.
So, any
Exactly.
thoughts on that?
Yeah, yeah, exactly. This thing, we had a group meeting that day. We have Saturday group meetings. It's very tiring. We work all day and have group meetings because we feel sleepy. That is the main challenge. Okay, so we were talking about it, and sir said that sir mentioned that we need to cut down the use of silence. Like silence are being produced in our reactions, so it's very difficult to throw out these silent waste products. And also in other
Yeah,
reactions we use pinacol boranes or catechol boranes or
exactly.
9 bbns also, and we have formation of bn bonds, okay, bpn bonds or sort of stuff like that. Or this is also very difficult to decompose or like throw away because these are silent waste products or borane waste products. So what sir has mentioned is that we have to find out other hydride donors which are soft enough to deliver the hydride to that carbamate center, right? The main mechanistic key is that you can see that the hydride is being transferred, and another driving force of the reaction is the formation of oxygen silicon bond. It's pretty strong, okay,
That's right. Yeah.
it's pretty strong. So we have to find out a center which is sort of does the same type of reactivity. We have not been able to like do so, but we are trying. Let's see how it goes. We will try to cut down the formation of this siloxanes or the boron oxygen boron compounds.
Yeah.
Till now I can comment on that only. Let's see how
Yeah,
it
that's
goes.
yeah, yeah, yeah,
Yeah, yeah,
yeah.
it's difficult,
Okay, yeah,
it's difficult. Yeah,
yeah, sure. Okay, thanks.
yeah, yeah, thanks a lot for the questions. Yeah.
Oh, no, 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 no. It was just go ahead.